paper, all right? Midterm paper. They write something on the board for you. The score is in a range of 43 to 96. If you want to know how I think this affects your grades, I think if you have anything better than, let's say, 70, 72, 73, doesn't matter. Let me call it 73. I would say these are, A plus, A minus kind of a work. And this is, I think, what's expected if you are a student studying this as your major field. And if it's better than, let's say, I'll say 50, I would say that is B plus, B minus. And I think that's quite good understanding of subject if you are a circuit designer or some other field, mechanical engineering. I think this is a very good understanding of the device technology. If you're less than 50, I would say need more work, all right? And we'll see what you do in the next exam and homework and others, okay? So this is the kind of grading that I think I'll follow, all right? Okay. So we will not grade on curves. And if you get a chance to help some friends in the class to improve his or her grades, by all means do that. All right, I'll pass this out in no particular order. Anwar. Turi is not here. Okay, I'll get Rasuram. Paper. Paris is not here. Okay. Haken? Well, why don't you take a moment to look through your paper. If there are some questions you want to bring up for discussion right now, we can spend a little time doing that. And you will also have a chance of discussing that in the discussion hour. Now, why don't we do that? I will ask you to study this paper during the break after today's lecture, and we can talk about it during the discussion hours. Okay? All right, let's do that. Okay, instead, now we go on to the to today's lecture. Now I'm following the order in the textbook. After device modeling, the textbook move on to talk about PMOS. There's a special section for 5.8 called PMOS. We actually have talked about PMOS on, I think a little bit during the lecture on the mobility. And so here we kind of just add a little bit more information, I suppose. One thing is that, roughly speaking, the whole mobility is about 1/3 of the electron mobility, roughly speaking. All right, this is not exact relationship, but whole mobility is about only 1/3 of the electron mobility. The saturation velocity of holes, however, we said, is not that different from the saturation velocity of the electrons. It is still smaller, percent, maybe even 30%. All right, of the electrons. Okay, and it's because of this difference. At some point, more than 10 years ago, people used to predict that when channel length gets very small, N channel and P channels ID set will become nearly identical. Can you see where that kind of projection would come from? It comes from the idea that eventually current will be determined by saturation velocity, not determined by mobility. Is that right? And in reality, do you know what has happened with all the device scaling today? What is the ratio between the ID set of N channel transistor and p-channel transistor? You know, is it becoming close to 1? It's not, all right? It has stayed about 2 and fluctuating, in fact, a little larger than 2. So the gap is not closing that much. So this gives a good question for you to think about. You know, you have studied the model for the ID set, and including the velocity saturation, we certainly did not ignore that. And I did tell you that it's an accurate model. In other words, presumably will predict this ratio of 2. I have not done that numerical example with you in class, and I guess you have not had a chance to do that in the homework either. So why don't I leave that to you as something to think about. Again, if you know, necessary, we can bring back for discussion in the discussion hour. Why is it? Why is the N-channel transistor current and P-channel transistor current, why are they not approaching each other? Why? In other words, it seems that mobility continues to play a role, right? So how can you understand that? All right, but that's a fact, okay? That mobility differ by about x3, saturation velocity differ by only about 30%, and the current happens, as a result, the current happens to be about a factor of 2 different between the two, okay? Now, there are 2 kinds of p-channel transistors. One use p plus poly gate, and that kind of process will be called a dual poly process because p-channel transistors use p plus poly gate and n-channel transistors use n plus poly gate. So there are 2 kinds of polysilicon in this technology, so it's called a dual poly process. Now, if p-channel transistor and n-channel transistors both use n plus poly gate, it's called a single poly process, okay? All right. And let's see. The single poly process used to be the standard. This used to be standard. But now it's only used in cost-sensitive products such as DRAMs. For other applications, digital and analog, the dual poly process is standard. And the reason is a short channel effect makes it difficult to make short channel transistors using n plus poly gate for P MOSFET. And why don't we wait a few slides before we see why that's the problem, okay? Now, as far as the dual poly process is concerned, the 2 transistors in that process, the n plus poly NMOS and p plus poly PMOS, they make a very close twin. In other words, everything we learned about n plus poly NMOS, by the way, n plus poly NMOS has been our default transistor in this course, right? Kind of a benchmark. We always assume we are talking about n-channel transistor as n plus poly. And the reason is that if you understand what n plus poly n MOSFET, you automatically understand p plus poly p MOSFET. These 2 are very close to each other, okay? Just change the sign of voltages. That's about it, all right? On the other hand, if we talk about n plus poly p MOSFET, all right? That's the 3rd transistor, 3rd kind of transistor. And if you don't do anything special, in other words, even use a lightly doped substrate, by the way, the standard doping for PMOS transistor has to be N-type substrate, of course, right? Even using lightly doped substrate, you already has a VT that's about minus 1.2 volt. It's too large a number. We don't want minus 1.2 volt. We usually want minus 0.4 volt, let's say. Now, if you do the same thing that you would do to the using the following the duality with n plus poly NMOS, you would then increase the substrate doping. If you do that, then the threshold voltage becomes minus 1.5 volt or something like that, minus 1.6 volt. It's even far from what you want. All right? So therefore, for this 3rd kind of transistor, we do something special. We actually implant counter-dope the substrate It's a very unusual approach, all right? We would put boron into this N-type substrate in order to bring the threshold voltage down to a low enough voltage. By the way, it's very difficult to do that. That's why the industry has moved away from that. But when we are still making minus 0.7 volt transistor, that's the way it's done, all right? We'll implant some boron to bring the threshold voltage from minus 1.2 volt to minus 0.7, and that will be done, okay? And so we would implant boron in order to bring the transistor down, threshold voltage down, okay? But when I say down, we mean less negative value, closer to 0, right? All right. Now, as far as the mobility model is concerned, if we're talking about P plus poly PMOS, the duality with the M plus poly NMOS tell us the E effective is still equal to this. All right? And perhaps I want to, probably it's better, although it probably does not make a difference, maybe it's better to add a absolute value signs, because we're not worried about signs. We can certainly figure out what signs we're dealing with, all right? For the third type of transistor, that's M plus polygate PMOSFET, and this is something we have seen before, that the vertical effective field would be equal to VG plus VT minus 2.4, 2.3 volt divided by 6 times Tox. So one very interesting fact is that comparing these two types of PMOSFET, comparing these two types, the top kind is good for short channel effect, and we haven't yet talked about why. Good for short channel effect. The bottom kind gives us lower E effective and therefore higher mobility. For a given VG, if these two type transistors have the same VG, they have the same VT, they have the same oxide thickness, that's usually what the engineers want, designers want. They say, I want to operate this transistor, this VG, I want this VT, and I would like to have this much current, therefore I want this much oxide thickness. So if you design two p-channel transistors meeting that same spec, same VG, same VT, and same Tox, this M plus poly PMOS actually will give you more mobility because it ends up with a smaller vertical field. All right? Okay. This does not necessarily mean that the current does not follow along the surface in strong inversion. In fact, I think you have done homework which shows that it could still be flowing along the surface. But just because vertical field is lower, we just have significantly larger mobility. In other words, if we plot mobility versus VG, we expect these two type of p-channel transistors to show two mobility curves that are parallel to each other but shifted by 2.4 volt. Now that's a very large difference, considering today the whole power supply voltage may only be 2.5 volt. All right? So certainly the effect is quite different. So we should really think back about this M plus poly PMOSFET with some nostalgia. You know, we are giving up something with very high mobility. Why is that? Well, it has to do with the short channel effect. All right. The newer type PMOSFET using P plus poly, so-called surface channel, has better short channel effect than the M plus poly MOSFET, the so-called Berkeley channel PMOSFET. All right. Now, how can you understand that? The easiest way to understand that is to look at this quantity X depletion. Simply because we are counter-doping the substrate with a P-type layer, we end up increasing the depletion region. Can you appreciate that? Just by doing that. I mean, this thickness cannot be too thin. We just don't know how to implant a dopant that's thinner than, many hundred angstroms. In fact, with little diffusion, they can easily go to 1,000 angstroms. All right, have to really try hard to keep this at a few hundred angstroms. And then you add this depletion, and part of the N is depleted, P is also depleted, so you just have larger depletion region thickness. Is that right? Whereas for the N-channel transistor, in fact, I probably should take this away just not to confuse ourselves. You know, with the newer style of retrograded well, we shouldn't really think we have a boron implanted layer in the N-channel transistor, although earlier the N-channel transistor indeed had a boron implantation layer near the surface to bring the threshold voltage up. Okay, today we don't do that anymore. We dope the well so heavily that even without that surface boron implant, we already got a VT we want, in fact more than what we want. So we actually go to the retrograde doping profile with the doping density lower near the surface. So in this case, then the depletion region width is smaller. Is that right? And we already argued why we want to go to retrograde, ideal retrograde doping that actually allow us to get 1/2 X depletion for the same VT compared to uniform doping. Remember that exercise? All right. We can get the same VT, but having half the depletion region width, comparing the ideal retrograde design and a uniform design. Okay, that's the basic benefit. So we know small X depletion is good for a short channel effect. Now back to this Berry channel case, we can certainly see that we're not going to have as good a short channel effect. Is that right? Okay, so that's that. By the way, you know, there's a benefit of having large X depletion in terms of swing. Do you remember? Swing tells us it's equal to 60 millivolt, 1 plus, do you remember what we say? We say it's a C depletion divided by C oxide, right? Right? So when the C depletion is small, namely X depletion is large, it's supposed to be good for swing. Is that right? Right? Now, if I tell you in reality, Berry channel transistor does not have better swing. If you really look at how they behave, they just don't have very good short channel effect, right? And also swing is really not better. Do you see a way to reconcile these two statements? The one statement is that X depletion is larger because we know the short channel effect is worse. The other statement is swing is not better. Do you see any way to reconcile this? Give it a try, please.
Is that because of the boron doping
Very
for
good.
the leakage?
Yeah. I think in homework you were asked to look into this question. A Berry channel transistor in the strong inversion case, when the VG is large, strong inversion, actually you can show holes still cling to the surface, flow at the surface. But if you look at the case of VG equal to 0, low VG, VG equal to 0, indeed, this is the picture of the energy band diagram. All right? So the subthreshold leakage is not flowing at the surface, but at several hundred angstroms below the surface, perhaps. Well, we don't know how many hundred angstroms, maybe only 100 angstrom below the surface. So what are the relevant capacitors that determine the swing? Is it really the capacitance between this oxide and the capacitance of that whole substrate? Or really should be the capacitance between the gate and wherever this inversion layer responsible for subthreshold current is? The ratio between that capacitance and the capacitance to the substrate. So which do you think is the correct answer? Is the top one or the bottom one? Right? If you think about the meaning of swing, why swing determined by this voltage divider? It's because we want to know how much does this potential, how many millivolt do we have to put on the gate in order to change this potential by 60 millivolt, right? because it's this potential that controls how many holes are in this subthreshold inversion channel. Is that right? Not this potential. There's no holes here anyway. It's the potential of this EV and the separation between that and the Fermi level that determines how many holes we have in the subthreshold conduction channel and therefore how much subthreshold current. Does that make sense? So when you look at this, you will agree that subthreshold characteristic is not good for this transistor either. Okay? You can try, of course, to make it good by making the depletion even wider depletion region. Of course, you can do that by doing things like making this doping very light here, for example, and have doping very light. Yes? Yeah? Or even make the PN very graded. And in fact, there was even an IEDM paper talking about, this is the way to design the retrograde transistor because it gives you a large subthreshold swing. And, you should be able to reject that statement, that design outright. Doesn't make sense, right? It makes sense for long channel transistor. But once you go to short channel transistor, your short channel behavior is going to be so bad. Right? Why do we want good swing? It's we're trying to get low leakage current at VG equal to 0. But short channel effect just means we cannot get that. Is that right? Short channel effect means we're going to have a large leakage at VG equal to 0 while channel is short. Right? Okay. All right. So let's then move to a different topic. This topic is not in the textbook. Textbook did not talk about lead trip, but I think it's important that we mention this in this course. And I mention at this point because lead trip only happens when you N MOSFET and P MOSFET together on the same chip, namely in the CMOS transistor, in CMOS technology. And in fact, these two type transistors has to be close to each other. That's where you have a potential vulnerability to a phenomena called a lead trap. First, a description of the symptom. What is lead trap? Now, it's known that if you take a CMOS circuit and often for some unknown reason, a large current start to flow between the VDD node and the VSS node. It's as if the chip has become a short circuit between the VDD and the ground. All right, and usually so much current flows into this chip as a result of that large current flow that something in the chip actually blows up. Aluminum line melts, for example. So lead trap usually is the destructive problem. All right. And now, of course, we understand what's going on, and we know when thing may go into lead trap. That's when there's some particular trigger, and I'll just leave that word trigger there for a while. We'll come back to talk about it. So let's just quickly go explain why a CMOS circuit sometimes can appear to be a short circuit between VDD and the VSS. All right, how can that be? Well, it can be because turns out in the CMOS circuit there is a parasitic PNP transistor and parasitic NPN transistor. This PNP and NPN transistor are connecting in such a way that they go into a positive feedback. First, let's identify these transistors in this cross-section. Then we talk about why they can go into a feedback loop and cause a short circuit. All right, just look at this cross-section and identify the MOS transistors first. There are two MOS transistors. One, we have a P-channel transistor, N-channel transistor that's represented by this N plus source and N plus drain. All right, so this is N plus source, this is an N plus drain. Okay? Yeah, there's a channel between them. On top of the channel is an oxide and a gate. All right, so I shade this gate. This is the gate of the N-channel transistor. To make a P-channel transistor, we first diffuse an N-type well into the P substrate. After we have made N plus N well, then we can create a N plus drain, a P plus drain, and P plus source, and a gate for the P channel transistor. So we now have a P channel MOSFET. Is okay? All right? So some subtle details. In fact, mainly for latch-up, well, let me just say, firstly for latch-up, all right? It's also good for other reasons. We actually often provide surface tie to the well, let's say the P well, N well. We create N plus diffusion to make ohmic contact with N well. And often the source is grounded to the substrate, often, all right? We do that. But right now, let me not emphasize this. You can just ignore what I just said for now, all right? And so let's just look at the basic. We will go back to the, okay, this MOS transistors with the N-channel transistor here, with a P-channel transistor here. These two transistors are connected in a inverter circuit, which means the gates of these two transistors are connected together and input voltage is applied to the gates. The drains of these two transistors are connected together and called output. So if I draw the circuit diagram for this inverter, this is what we look at, all right? The two gates of N-channel and P-channel transistors are connected, and the voltage applied to that gate is called input, Vin. The two drain nodes of the two transistors are connected together, and this voltage is called output voltage. The two source nodes are connected to the two power supply leads. One is the VDD, one is ground. These are the two source nodes. So the source of the N-channel transistor is connected to ground. The source of the P-channel transistor is connected to VDD. Is that right? So that's the basic connection of a CMOS circuit. Simplest CMOS circuit would be an inverter. Any questions about this cross-section? Now let's identify the parasitic bipolar transistors. There is a PNP bipolar transistor in this vertical manner. P connected to the VDD, N is the N well, and P is the P substrate. It makes a vertical PNP transistor. You see that? All right. Also, there's a lateral NPN transistor made of the N, which is connected to the ground, and the P is the well, and the N well, P substrate, let's say, and the N well. So N plus source, P substrate, and N well makes a NPN transistor. What's interesting is that this well serves both as the collector of the NPN transistor as well as the base of this PNP transistor. You see that? The N well is the base of one transistor and the collector of another transistor. Similarly, this P substrate is the base of one transistor and also the collector of another transistor. And when we look at how these two bipolar transistors are connected, this is what we find. Again, let's just look at the basic bipolar transistor. Don't look at these other things that we'll add on later. All right, only two bipolar transistors. We have a NPN transistor. This NPN transistor is this NPN transistor. I'm sorry, I said wrong. This is a PNP transistor. PNP transistor. This PNP transistor is this PNP. The emitter of this PNP transistor is connected to the VDD, so we put that VDD. All right, PNP transistor. Now the base of this PNP transistor is also the drain of the NPN transistor. So the base of this PNP transistor is connected to the drain of this second NPN transistor. The base of NPN transistor is the collector of the PNP transistor. So the base of the second transistor is the collector of the first transistor. You see that? All right. Finally, the emitter of the second transistor is connected to ground. This N plus is connected to ground. So we connect to ground. So just concentrate on these two transistors. Don't look at this resistor and the capacitor for now. Now we can write down some simple equations for this bipolar circuits. All right? Okay, we first write down I1, the collector current of this bottom bipolar transistor. The collector current of the NPN transistor, IC. Collector current, IC. Collector current is always equal to alpha times the emitter current. Is that right? Alpha of the emitter current. And the emitter current is I, because, as I said, don't look at this N here yet, all right? We're going to introduce that later. Don't look at this resistor here. So the emitter current is really just I, is that right? I is the total current going to the power supply, okay? Let me call this, I don't know, I'll make it, why don't I do this right now? Let me, for now, just ask you to ignore this, all right? Later on, I'm going to put back on it, on the slide, okay? Right now, you just ignore these things. Ignore these things, okay? So, the emitter current is I. I times alpha gives us the collector current I1. That's the bipolar transistor behavior, all right? Alpha is usually a very large number. Mostly you would think this as 0.99, right? If not 0.99, at least 0.9, right? Okay. And what is this IL prime? IL stands for leakage, okay? That is, even if we did not have any emitter current, we know collector will still have some leakage current just because it's reverse bias. There's always some leakage current, all right? You will see why we want to carry that. This may be only picoampere, so it's not too important in this equation, but you will see why we want this, even though it's very small. It's a picoampere, we just want to leave it there, okay? Similarly, if we look at this PNP transistor, we can say that the collector current, which is I2, is equal to alpha times the emitter current. The emitter current is I1, is I, right? It's total current. We call that I because according to the Kirchhoff's law or the current continuity, whatever flows from VPP into this VDD into the circuit, I, must be equal to the current flowing from the circuit into the ground, which is I, right? So these two I's are the same I. Okay? Again, we also carry a very small leakage current for that reverse biased collector junction. Okay. Next, we're going to add these two equations together, I1 plus I2. I1 plus I2. First of all, we know I1 plus I2, based on Kirchhoff's law, is equal to I. You see this I divides into I1 and I2? Yes? Similarly, this I1 and I2 combine back into I later, in this bottom transistor. So we know I1 plus I2 is equal to I. So we write that down. I1 plus I2 should also be equal to the sum of the right-hand side terms of these two equations, right? So we add these right-hand sides together. We'll get I times alpha NPN plus alpha PNP. Is that right? Plus those two very small leakage currents. It's okay? Next, we look at this part of the equation. We have this I appearing twice. So we can combine these two terms of I, yes? So for example, we move I to the left-hand side, then becomes I times what? Times 1 plus alpha NPN, alpha PNP, right? So it's this term. 1 minus parenthesis alpha NPN plus alpha PNP parenthesis. So we divide it here. And right-hand side is only left with IL and IL prime. Following what we're doing? Okay, take a moment to see that. Confirm that. Is okay? Great. Now we are done. Let's look at this equation. Is it possible that under some conditions, a huge current will flow through this transistor? Will it flow through the circuit? Current becomes infinity. Is it possible? Is it possible? Right? Sure, it's possible. When alpha MPN plus alpha PMP is equal to 1, then current go to infinity. What does that mean? That means it doesn't matter what voltage we apply here. We don't need a very large voltage. Huge current will flow through it. And that's the basic physics of latch-up. All right? So let's now go back to think about the equivalent circuit and maybe understand a little bit what's going on from circuit consideration. I use the term feedback. That's really what it is. There's a positive feedback if you are familiar with concepts in control system, control theory, and you can think that way also. Anytime this loop gain is larger than 1, you get gain. All right? That's what it is. All right? And remember, I said larger than 1 does not have to be equal to 1. Actually, as long as it's larger than 1, then this I will keep increasing. That's what we're saying. Does not have to be equal to 1. If it's if this adds to be 1.5, that's even better. This is just increasing toward infinity. It's okay? That's why this is usually destructive phenomena. Current can be so large until some line gets blown away. Is that right? Okay? So don't be too stuck with this idea they have to be equal to 1. If it's larger than 1, it's even better. You have even more gain. Is that right? Okay? Okay, any question about this idea? Why current can suddenly become very large? Okay, so that's called a latch-up. And the condition is for these two gains add to be equal to or larger than 1. Then you have sufficient gain for this positive feedback. Then the signal will just keep blowing up, right? A little bit current coming in, let's say get amplified. This amplified becomes the input to the next transistor, gets amplified again. This amplified signal becomes the input to the first transistor, amplified again. That's why it goes to infinity. Is that right? Okay. So now you can see there's no problem for the current to be, for this inverter to be short circuit. The question becomes, why is it not a short circuit all the time? Why is only, as I said, sometimes this CMOS circuit appear to be a short circuit? Isn't the fact that for bipolar transistors, it's very easy to get alphas very close to 1, so that add to be usually larger than 1? The answer is yes, it's true. So how do you reconcile this? Well, it turns out the answer is not that in this bipolar transistor technology, in this CMOS technology, the parasitic transistors are lousy. Therefore, this lousy bipolar transistors don't have very large alphas. That's not a correct answer, all right? Their alphas are very good. But just to force that issue, let me ask you to perform this mental experiment. Let's say you go to your favorite electronics supply store, let's say Fry's, and bought a NPN transistor and PNP transistor, right? If you read the spec, guess what the spec will tell you about the alphas of those two transistors? They're going to be very large, right? 0.99 easily, right? Beta will be 100, okay? So you take those two transistors, take home, use a soldering iron, connect them in this manner, all right? The base of one going to the collector of the other, the base of the other going to the collector of the first, right? Now you apply whatever voltage, 5 volts, 3 volts you want between these two leads. Do you think you're going to find a short circuit, or do you think you'll find an open circuit? In other words, I take away this lousy transistor hypothesis, right? These are very good transistors. Do you know the answer? You have an answer. What do you think you get? Open circuit is correct answer. Do you want to say a little bit more why you think that would be the case? It's just a hunch? Okay, speak into the microphone.
It's because of those resistors.
All right. That could be right. Let's not get into the resistor either, but your answer is correct. Indeed, we're going to be talking about, you'll find an open circuit, not a short circuit. The reason is this. the alphas or betas of transistor are functions, or betas actually, of current, of the bipolar transistor current. You may remember a curve like this in somewhere you have seen, that when we say 0.99, we really mean here. There's a wide range of a current in which this bipolar transistor works very well. But if you look at very small current, let's say nanoamp or even picoamp, the current drops rapidly. Is that right? Okay. So therefore, when you don't have large current to begin with, actually this condition is not satisfied. Therefore, transistors put together in series in this manner does not give you a short circuit, does not give you a latch up. That's why normally a CMOS circuit is not in latch up normally. So we need something to put them into latch up, and that's the meaning of trigger. All right, we need a trigger to trigger it. What's that trigger? Triggers anything that momentarily brings the current large. How? Many ways. That's why I put this in capacitor here. For example, if you suddenly put VDD there, if you apply this power supply very rapidly, just the capacitive current is enough to allow current to flow through the circuit momentarily. Then the gain is large enough. Once it's large enough, it's going to positive feedback. Does not require this external trigger anymore, and just get into destructive latch-up. You see what I'm saying? All right. That's why before this problem is well understood, actually CMOS circuit designers, product engineers had a very hard time. You know, circuit just fail. Someone turn on the light switch in the room, and suddenly this chip just blows. And that can happen, all right? So now there are a lot of precautions. Sometimes you will even see circuit boards is designed in such a way that certain, for example, power supply is connected before this output voltage is connected, because our input voltage, our output voltage, because output you see goes to leads that you have no control of. You don't know what is voltages on this output leads, right? They can actually forward bias your PN junction, for example. That will certainly give you a transient current, is that right? A transient forward bias because of inductive noise, let's say. Right? So there are a lot of things that can trigger it, and therefore elimination of trigger is really not a good solution. Okay, designer did try that route to try to minimize the trigger, but you can never, prevent users to abuse the circuit. You don't know what they're going to do to the circuits. So the solution today is actually to make this circuit tolerant of a large trigger current. In other words, it may still be triggered into latch up, but it's going to require many amperes to trigger this circuit into latch up. If that's the case, then essentially you're safe. See that? Okay? So how do you do that? Well, you do that by realizing that if I can short circuit the base and the emitter, then I basically take this transistor out of commission. We don't have a real transistor anymore. In order to have a bipolar transistor operating, we have to have this emitter and base junction forward bias, say 0.6 volt. Is that right? Yes? Until this junction reaches that voltage, they essentially don't inject any carriers. So we don't have any gain. Is that right? Right? By the way, that's the reason why in bipolar transistor gain usually very small when you have small current. Small current, you're having recombination current and all those leakage current. They're not conducted by this forward bias, the junction. All right? Okay. So how can we prevent this junction to become forward biased? Well, you simply short it. That's exactly what we're doing here, by trying to put a very good ohmic contact to the body, right? So that this base, the body is the base, is that right? Substrate is the base. Yes? Yeah? And then we try to short this contact to the source. That's the body, that's the emitter. So we're trying to short these two leads. Okay? But turns out what happens is that doesn't work. The reason is that there's significant parasitic resistance just between here and here. So you may be able to short this portion of the body to the source. You cannot short this part of the body to the source. So that this part of the body and source junction can still be forward biased. See that? And that's why we have to model this with a resistor. We can never make a real shorts. If we make real shorts, then there will never be any latch up. But in reality, no matter how hard we try, we still have to remember that there's some resistance here. If there's some resistance, now the picture is different. When we suddenly apply a dVdt, let's say suddenly turn on the power supply voltage, for example, I used this example. Now, significant amount of capacitor current can be allowed because they will flow through these resistors. If they flow through resistors, then the transistors are not turned on. You see that? Because otherwise, if this is not here, when we suddenly apply a large voltage, say from 0 to 5 volts, suddenly this is forward bias anyway. You see that? It's a PN junction. You see the arrow? This junction forward bias. Normally, it's this junction that's reverse bias between base and collector, so there's no current. But because this junction has large capacitance, is that right? Finite capacitance. So when I suddenly raise this, apply this VDD, for example, I just plug the PC board into the slot with the power on. Let's say it's hot plug-in, suppose, right? Then there will be a large transient current flowing through this base and emitter junction. Do you see that? Yes? Any current flowing through the base emitter junction will mean there's a forward bias, right? Right? And that's what causes this latch up. But with this current can flow through this lead path. You see that? Then there will be no problems, yeah? Yeah? It's okay? So that's the example of how this helps with this one particular trigger mechanism. But other trigger mechanism is also helped, okay, by the same analysis, simply because very large current must flow through this before forward bias can be equal to 0.6 volts. For example, if this is 1 kilo ohm, this resistance, okay, then what? Then 0.6 milliamp will have to flow through here before we forward bias this junction. Is that right? And that's pretty good, 0.6 milliamp, by the way. So here's the question for you. Given that's the answer, is it good enough if we have a 1 kilo ohm here? Is that short small enough? No, because 0.6 milliamp is not that large a current in terms of transient in the circuits. It's not that large a current. I give you example. We want to tolerate ampere of trigger current. Turns out we cannot do that either. So very typical spec for trigger current in the company these days will be things like, say, 200 milliamp or something like that. You have to be able to tolerate that kind of trigger current before the transistor go into latch up. All right? Okay? Okay. In principle, if you can short out either one of these two emitter-base junctions, you would have succeeded. In practice, we cannot short out either one perfectly, so we try to short out both. Okay? That's what we do. And if you ever find a design with a floating well, that's a no-no. It's a guarantee of trouble. So a design rule checker will always look for any well that's floating. Right? You have to short that ground that either connected the well to a to VDD or connected to VSS. Is that right? Okay, that's called latch up. Now, so one way to reduce this resistance is to try to put the contact quite frequently in the well so that no PN junction is far from one of the well contacts. So there are design rules that may say every 100 micron or something at least, or even shorter distance than that, you have to have a contact. You cannot say I have a big well, I just put one contact, I've contacted it. You cannot. You have to think about this resistor. All right? And other times, people will then build a circuit on a P plus epitaxial substrate. And you pay some more money when you order the substrate, but it will give you better latch-up behavior. Why is that? Because this P plus material helps short out this resistance. See that? Okay? You have to remember, this is not drawn to scale. You know, these separations could be tens of microns, right? Between where you have the contact and the father's transistor somewhere, right? You cannot afford to put a contact with every transistor, by the way, okay? You put a contact maybe every 20 microns. So between this and another PN junction 20 micron away, there's a large resistance. But you can order an epi wafer with this epi fairly thin, let's say 2 micron in thickness. So this epi, P plus, kind of short out this resistance between the contacts and the P substrates. Can you see what I'm talking about? All right? Okay. So sometimes this is done to improve the latch-up behavior. It's okay? All right. Finally, let me mention one other thing. This is more realistic now for more recent thing. In the past, it's not so realistic. Turns out a latch-up behavior, if you plotting the IV curve, have 2 branches. One in the off state, that is before this condition is satisfied as a result of a trigger. The circuit is just an open circuit. That's what we want the CMOS circuit to be like. Once you trigger it, it goes into this branch. This is the short circuit branch. Very low voltage, and you get very high current. But what do we mean by very low voltage? Turns out it's not that low, very low voltage. If you start to ramp down in this branch, assuming aluminum line hasn't blown out, all right? Assuming you can still study this branch. If you ramp down the voltage of current, this branch is only sustained up to certain minimum voltage, minimum current, called holding voltage and holding current. Below that, latch-up cannot be sustained. And you can see why it's like this, right? If this holding current is too small, this 2 junction becomes shorted again because current will flow through the resistor. Is that right? So it has been the holy grail for a long time for technology designer to design the CMOS technology so that holding voltage is actually larger than VCC or VDD. Right? If that's the case, you don't have to worry about any trigger or anything. If VDD is actually smaller than the holding voltage or the other way around, then that would be really the best, the surest way of stopping latch-up. Is that right? And has been very difficult to do that unless you do something really fancy like buried layer, M plus, and P plus layer. But you know, with power supply voltage dropping, that become, I think, somewhat a more realistic thing to do. So certainly something new thing worthwhile start to think about how we can, what controls this holding voltage, what's the theory behind that, and how can we increase that and make that even larger than VDD. Okay. And by the way, you can analyze the holding voltage, holding current, essentially using this equivalent circuit, actually. All right? Okay. So the condition for latch-up is alpha NPM plus alpha PMP larger than and equal to 0. This doesn't really necessarily tell us about, you know, how to kill the alphas, as to tell us there's a need for a trigger, number 1. And number 2, also can be used to understand the concept of why these transistors help, because I'll leave this to you as a sort of exercise for the bipolar transistor consideration. Is can you interpret this resistor shunt as a way to reduce alpha? Maybe you want to think about it a little bit, and particularly easy when you start thinking about small transistor equivalent circuit. You know, the pi circuit or whatever equivalent circuit. When you add a shunt between the emitter and base, can you see it's effectively reducing alpha? Right? So, in a way can be understood what that's doing there. Okay. Okay. All right. I think we'll stop there about latch-up. Okay. I already mentioned why adding a P plus epi is helpful sometimes. Okay, any questions about latch-up? Any question? Any question about latch-up? No? Okay. Great. Let's move on to another section. The textbook called this two sections, 5.6 and 5.7. I don't remember the actual title the textbook used for these two sections, but I'll just call this group of topic MOSFET scaling, all right? In a way, a little bit of summary of some of the issues about scaling we have talked about already, but try to put this in a way that's a little more organized, okay? All right, so scaling does have some several historical interpretations of the word scaling, but today I think most people think of scaling just meaning size reduction. So let's just use that concept, all right? Reduce the size of MOSFET transistors. So what's the goal for doing that? What are we trying to do? We're trying to increase the packing density, right? So that we can build larger electronic systems and we can build them in smaller chips, therefore reduce costs. So that's still the number one goal for scaling. Really, what it is to increase the packing density. Okay, all right. And secondly, going to a lower level, what we're trying to do is we want to increase ID, and we want to reduce capacitance, right? Well, you probably can see why reducing the transistor size, for example, make channel length smaller, may give us larger ID. So that certainly is a larger drain current. So that certainly could be a goal that can be accomplished by reducing the MOSFET size. And I think you can also see by making transistors smaller is potentially a very good way to reduce the capacitance of the transistor and therefore of the circuit. And why do we want to do those two things? Because this will increase the speed of the system of the circuit. Is that right? You have a small capacitance, you have large current, then you can charge and discharge the capacitance fast. Right? Okay. And by the way, when we say reduce the capacitance, we don't just mean reduce the capacitance of the transistors. By making transistors smaller, indeed reduces the capacitance of the transistors. But it also reduces the capacitance of the interconnect. Do you see why? Because if you make transistors smaller, the circuit is smaller, interconnect becomes shorter, right? Right? If you use larger transistors, the chip is larger, interconnect will have to be longer. Right? So that's clear. So you can get larger speed and you can reduce power because power is reduced to capacitance. I think you have that concept, right? So that's the goal for device scaling. And we want to scale devices as much as possible, but subject to certain constraints. So what are the constraints? What's preventing us from making the transistor as small as we want? First of all, there's technology. Specifically, lithography definitely is a limitation. There's no question about that. And but in terms of what this class is concerned about, turns out leakage current is a concern. All right? And finally, is the reliability. So that's all. Technology is a constraint, leakage current is constraint, and reliability is constraint. Now, what do we mean by leakage current? We mean leakage current, we can say we want any leakage current, right? The unit would be nanoamp per micron, right? It's pointing at leakage current, nanoamp per micron. You may have seen these units before. Maybe we didn't highlight this. But it's really how many nanoamp flows through this transistor at VG equal to 0 for each micron of W. Right? We want to minimize that. Right? And what are the mechanism for this leakage current? There's a subthreshold current, right? And it's related to the question of VT choice. If we choose VT large, this current is small, but circuit performance is slow, right? And it's related to VT roll-off. After we have chosen that VT, there's still a problem of VT roll-off, right? And it's related to the concept short channel effect, or DIBO, right? And there can be punch-through, which we use this term to refer to current flow that's not at this interface, but some subsurface paths. Is that right? And GIDO is also a leakage concern. PN junction leakage is also a leakage concern, right? So those are all the leakage we have to worry about them. Reliability, well, that's because when I make the transistor very small, you can worry about things like oxide breakdown. There's something called hot carrier effect. Both of these will have a chapter each in the textbook. We'll talk about later in this course. There are things like electrostatic discharge, just because oxide is so delicate. If you touch the lead, often the transistor will just fail. Of course, they don't today because engineers do something to protect against the electrostatic discharge failure. But you can see that ESD is a problem. Electromigration, meaning the metal wire can also fail. What makes reliability both interesting and difficult to deal with is, by definition, reliability means things that happen or may happen years in the future. It's not something that you can see today. And for that reason, it's a particularly difficult group of problem to deal with. In some sense, harder than, say, speed of a circuit. Because after all, if the speed doesn't meet spec, you will know it before you sell to the customer. Reliability is something that might happen years down the line. So how do you deal with that, right? And the concept related with reliability will be things like lifetime. You can say you want to guarantee lifetime, guarantee 10 years. But that by itself is not a meaningful thing, because no one can guarantee absolutely no failure. You may guarantee a failure being less than this much percent in 10 years. Or this brings us to something called a failure rate. Failure rate has units like how many failures per chip hour. Right? You can imagine the meaning of chip hour, like man-year, that kind of concept, right? Right? So typically, the unit used is 10 to the minus 9 failures chip hour. All right? That unit has the name called fit, so 1 fit. So companies often are trying to get 10 fit. Some even say they are getting less than 10 fit. It's very difficult. 100 fit means about 1% failure. 1% of failure in 10 years. Right? So 10%, 100 fits is probably what most user will accept. That means 1% failure in 10 years. Right? Okay, in 10 years. If the failure is uniformly distributed in time, then that gives us this much 100 fit of failure rate. All right? But most companies will show a reliability handbook that says it's less than that. So that's the kind of reliability goals. All right. Okay. Now, when we talk about performance, we always use the CMOS as the example because that's the only kind of circuit in use today in the MOS technology. CMOS is equal to NMOS plus PMOS in the same circuit, right? We have seen how these are fabricated. It involves the use of this well inside the substrate, right? And the simplest circuit will be an inverter. We're going to use inverter as the analysis of this discussion. And inverter is made of a p-channel transistor, n-channel transistor, connected in this cascaded arrangement with input connected to V-in and output is out. All right. What's interesting about this circuit is that if V-in is zero, then the p-channel transistor will be on and n-channel transistor will be turned off. The current will flow from the VDD through the p-channel transistor and charge the load capacitance up so that V out will be equal to VDD eventually. All right, but there's a time delay for this output rise. When the input voltage is equal to VDD, the n-channel transistor on, p-channel transistor off. That n-channel transistor will then discharge the capacitance on the output node to ground until the output voltage is equal to 0. Okay? And there's also a delay involved. Before we talk about the delay, let's just briefly mention the power of CMOS circuit is equal to VDD squared times C times the effective switching frequency. This is because every cycle of switching, a charge Q equal to CVDD flows through this power supply, is supplied by the power supply. So on average, the current therefore is equal to Q times F, because Q is the charge per cycle, and if there are this many cycles per second, the current is equal to Q times F, therefore, is equal to C VDD times F. And the power is equal to I times V times VDD. Therefore, is equal to C times VDD squared times F. Okay? All right, so that's the power loss of the consumption of the CMOS circuit. Now let's talk about the speed of the circuit. We talk about the rise time and the fall time, and this all refers to the output. Let's think about rise time. Rise time, the time it takes for the P MOSFET, for this PFET, to charge this capacitance C from charge up, let's say. Okay? How long does it take for this transistor to charge up this capacitance? Well, you can see that, roughly speaking, maybe I should say roughly, don't worry about the detail for now, approximately is equal to VDD times C divided by IP. What's that? VDD times C is the charge we have to put on this capacitor, right? Charge divided by current is time, right? And the charging current is the PMOS transistor current. We'll call it IP. You see that? So approximately, generally speaking. Is that right? Okay. And that's why we say in order to make the circuit fast, we want to do two things. We want to make the transistors carry a large current, and we want to make the capacitance very small, right? By the way, here we also see the third thing we can do. We want to make power supply voltage small. But of course, when you make power supply voltage small, the current also gets smaller, so it's not clear that you gain or loss in terms of the speed. Usually we lose something. We're losing speed if we use smaller power supply voltage. Okay? But we still want to use small power supply voltage anyway because we can reduce the power dissipation by using small power supply voltage. It's very important that we use low voltage, right? So we use low VDD to reduce P. This is very important, right? Very important. All right. So for given VDD, then all we can do is reduce C and increase I in order to reduce this rise delay time. All right. So large current ID gives us good speed. Similarly, there's a fall time. That is, how long does it take for this N-channel transistor, this NFET, to discharge the capacitor? And that's VDD times C divided by IN. All right? So there's a concept called the delay time. Delay time basically is the average of the rise and fall time. So in one cycle, we have a rise and fall. So the average of the two is the delay time. All right? So delay time, therefore, is equal to VDD times C 1 over IN and 1 over IP divided by 2. 2 is this average concept. Okay? What is that eta? Eta is the fact that, this top two equations are all approximate. We don't really know if they're exactly equal to. To be frank with you, we don't even know where to take IP and IN. Do we take it here? Do we take it here? Do we take some kind of average? Right? Average is probably an easy way to answer. But how do we average that? It's too complicated. So instead of average, we're going to force them to be ID set. ID set of N-channel transistor and ID set of the P-channel transistor. If we do that, certainly we cannot force this eta to be 1, right? So we put this as an unknown. And then we compare this relationship with SPICE simulation. You see, you can easily construct some sample circuit for SPICE to simulate the delay time, simulate some ring oscillator delay times. Very easy, right? Because you perform the SPICE simulation, you can also plot out the SPICE model to see what ID set N is and ID set P is. You see what I'm saying? Right? If you know the ID set, you know the capacitance you put on in your simulation circuit, your load for your ring oscillator, you know the VDD used, and you simulate tau, then you can figure out what eta fits a broad range of the circuit you simulate. And turns out, when we did that, we find out 2 works very well here. So therefore, it's 4, okay? If you read some of the reading material in the reader that you receive at the beginning of the semester, you may see some papers called 3.8, 3.7, some called 4. 4 is just a good round number. Is that right? Okay, so you can obtain this number by comparing this with SPICE simulation. Once you have done that, now you can ask, what's going on here? Why we should not divide this by close to 1, but rather close to 2? Well, it's hard to say exactly what, but basically, why it's exactly 2. But we can appreciate, I believe, that does not require, the rise time does not require this capacitor to charge all the way from 0 to VDD, right? By the time to get to half a VDD, for example, the next stage of ring oscillator is already switching. Won't you agree? Right? Just think about the transfer characteristics, right? Right? So that will explain why this may not be another factor of 2 comes here, right? Right? That's why SPICE will give us maybe 3.8, 3.7. You see what I'm saying? Okay. All right. So, you know, once you know that, you may be able to go back to argue this way, give that interpretation. Well, it's really the time for it to rise to have a VDD. Okay, that's one way to interpret that. But this came from this SPICE simulation. Do you know what I'm talking about? All right. So this, I put a box because it's really worthwhile to remember this equation. This is the basic model for the speed of a CMOS circuit. An inverter delay is equal to VDD times C over 4, 1 over ID set N, 1 over ID set P. By the way, I did not emphasize this for you. This is measured at VG equal to VDD. All right? So sometimes in the literature called ion. You can say ion N and ion P. So the model cannot be simpler than this anymore. Is that right? We don't even need to know this IV curve. We only need to know ion at VG for a transistor. And certainly you have the model for this ion. Right? Okay. Let's put those ion equations in this equation. Try to do this a little bit better. All right? And okay. So why sometimes people actually I will not go into this today. There's no time. You can certainly ask questions when we have discussion hour. You know, well, let's not. Okay, you can ask questions. Get to the. All right. Looks like we're almost at the end of this lecture. Why don't we just take a 7-minute break now, and we can come back. Perhaps go through a few more of these slides. If you don't have questions, you have questions, we'll take your questions, perhaps about the midterm exam. Okay, take a look at the midterm exam paper. We'll meet in a few minutes.